So thank you so much for your attention, and I welcome your questions.
Thank you very much, Helen. That was very interesting. Dr. Trounsend.
Helen, as usual, it's very impressive what you do. I was thinking that, as I recall, and my recall isn't that good on some of these things, but in cancers, I think telomerase is active, and so you get an extension of telomere length in cancers. When you're recommending that we think about extending telomere length, are you all concerned about shifting in towards a cancer phenotype?
No, for two reasons. One is that skeletal muscle and cardiac muscle are really not prone to cancer. There are no tumors of the heart that have been reported, and in the skeletal muscle, it's extremely rare and happens in certain childhood diseases, but it's extremely rare. So there's an anti-tumor environment we don't totally understand, and it's worth studying. It's even known that if you bulk up muscles and you have a tumor of a different kind elsewhere in your body, that the progression of the cancer is slowed. So something produced by muscle is anti-tumorigenic. So that's one reason. Another is, I think we need to devise methods for extending telomeres that are short-term and that are targeted. And we're working on that in our lab, a way to do this in a safe way, where you're not interfering with the cancer phenotype, because you're just targeting the cells you want, and you do a very short-term treatment. And so far, we have indication that this can work in certain cell types. And that, I think, will enhance the use of stem cells generally. So many times, people are making stem cells for different tissues, and by the time they get the cell they want, the cardiac cell or the liver cell, it croaks because it's gone through too many rounds of replication. If you could give it a dose just for 3 days of something that extends its telomeres by the amount that you lose in several years, I think that would enormously enhance regenerative medicine. And that's an approach we're working on in our lab.
Just one other question I have, that it's been rather difficult to target muscle cells in muscular dystrophy because you've got to give so many injections. So you've got thoughts about delivery systems here that are a little different to what people think about?
So you're right, delivery has been a great problem. In fact, I did clinical trials with Duchenne muscular dystrophy with myoblasts, which are the progeny of muscle stem cells. And they did no harm. They integrated into the muscle, but they did so very localized. And the problem is that 10% of your body is muscle. So how do you treat all those muscles? Right now, with methods that are available currently for directing the stem cells, they stay locally, and it would be a matter of improving the quality of life, say improving the function of some hand muscles to help. But that's an amelioration, it's not a treatment. I think what we want in the long term, so for the other diseases I was talking about, those would be localized. You could treat a small muscle, an eye muscle, a jaw muscle, a urinary tract muscle to prevent urinary incontinence. There you could have a localized treatment and it would work very well. In the case of Duchenne, you want a more disseminated approach. So you need to think of a way to try to deliver these maybe via the circulation and have them targeted. That's one approach, easier said than done. But there are ways we're thinking about it. And then we're also working with bioengineers to develop what we're calling nanonoodles that are a way to deliver the cells very broadly and also link different kinds of factors that enhance stem cell function and also enhance the environment, making it more friendly to stem cells. And I think the combination of bioengineering with stem cell biology is going to be the next step in treatments, because delivery is a major problem not only for muscle stem cells, but for many stem cells, as you well know. So those are the approaches that we're taking.
So it was very clear the role of the satellite cells and how they would, replace the skeletal muscle. Is there something comparable in the heart, a similar cell that's a stem cell?
So the stem cells in the heart are still highly debated. as I'm sure you know. So some people report that there are stem cells, some people report there are not. I would say there is not consensus right now on whether there are or not and how well they function in regenerating the heart. And so whether a stem cell treatment in the situation of the heart is what would be recommended, I think is still a matter of debate. And for the heart, it may be that you want to do something different. So, but the jury's out.
Helen, it was beautiful work. Your studies you reported were in G2 mice. If you take them out further generations, is there a progressive further shortening of telomere length?
Yes.
And is the phenotype just exaggerated? Or?
Right. So we didn't take them out further for a good reason. So many people have looked at this as an aging phenotype before. Just getting rid of TERK or TERT leads to generalized aging and shortening of telomeres throughout the body. And that's how they proved that telomerase is key in telomere lengths for not aging early. So there are early aging models. G4, G5, generations 4 and 5, have greatly shortened telomeres everywhere, and now you have a systemic disease. You have liver disease, blood disease, so ubiquitous. And so our theory was that it would be specific to the tissues that require dystrophin if we did it early, because, and that's key, so that we don't have an effect on other tissues that complicate the whole thing. So we're more mimicking the human situation where it's only the cells that require dystrophin and have somewhat shortened telomeres that are affected. This is not a ubiquitous systemic effect, which would be a reflection of aging, which happens by generation 4 and 5, and is used widely as a model of aging. But no one has done this in this way, looked at a single gene defect in conjunction with slightly shortened telomeres. And I predict that will give us better models of the human disease, certainly for the heart, but probably the liver and many other diseases that have not been well reflected in the mouse model, and that telomeres play a greater role. And they could do it in many ways, not just highly proliferative tissues, but as you remarked, low proliferative tissues such as the heart.
Is it possible that, I've never heard of telomeres before, so bear with me, but I'm wondering if there's any equivalent function or dysfunction and role in neurodegenerative disorders of any sort, because there is oxidative stress and mitochondria and so on at play. So.
I would bet that there are. I don't think it's been studied. If you just look at the aging model where you have shortening telomeres, then you won't see it. So you have to set it up in the way that we have. So I don't think it's been studied in that way, but I would predict that it will affect many, many different tissues. And this is a more humanized way to look at the loss of function of a particular gene product.
Might it be used as an earlier, what's the word I'm looking for, indicator of disease? Everybody knows this word, I can't think of it, but that you might look to that to see if someone's at risk for
There are thoughts
Parkinson's
about that, actually. I've been talking to some colleagues at Stanford, and there are some drugs that cause telomere dysfunction. And so it might be a way to predict whether you're going to get cardiac symptoms early, and these drugs cause the telomeres to be shortened, and I don't know the details. But I think it's something that may prove more useful than we think. And that one might be able to even look in the blood cells of people who've been exposed to certain foreign agents or drugs to see if they have somewhat shortened telomeres, which might predispose them to, say, cardiac disease.
Thank you.
So I think that's a very good question.
Thank you.
Anne-Marie?
Thank you again, Helen, for this spectacular presentation and for all your work in general. In your hope of maybe finding a way to help the disease with stem cells, you mentioned one of the major challenges being the delivery of stem cells. Are there other key challenges that you see that you have to resolve before thinking about clinical trials?
Okay. So for muscle, we're lucky. I think for most cell types, it's a huge obstacle. How to deliver nerve cells to the brain, how to deliver them to the spinal cord, get them to not only do damage when you put them in, but wire and fire correctly with the cells that are local. Delivery is a huge problem for most. We're lucky with muscle. It's more like blood. you can put blood cells in and they'll function fine. And with muscle cells, they know how to find their way. I didn't show all of this, but they find their way to that muscle stem cell niche. They replenish the reserve so that you have stem cells long-term after you deliver them. And they know how to find their way to integrate into the muscle fibers as well. So delivery is not a problem when you want to do it into a localized muscle. Delivery is only a problem if you're trying to get all the muscles of the body. That's not easy. But I think localized treatment with muscle stem cells is extremely possible and something that we can do very soon in clinical trials. So we are at the stage now where we're characterizing the human muscle stem cell, and we've developed these various strategies for enhancing stem cell function in the mouse that we want to apply to the human. And then one could treat these localized muscle disorders, which, as I mentioned, beyond the dystrophies, and some of the muscular dystrophies are more localized, so those could be treated with stem cells in conjunction maybe with the missing gene. But these smaller muscles, swallowing muscles, different things that happen with aging or post-trauma could be treated in this way, and with your own stem cells. So you could take say, this is what I'm envisioning, a biopsy from your leg, and you enhance those stem cells and you put them where you need them in another muscle. So the ocular muscle or the jaw muscle or something of that sort. So I think it has multiple applications, and we're very lucky with the muscle that it knows it knows its identity, knows where to go. It can replenish the stem cell reservoir and regenerate the tissue.
Could that be true of, say, ALS or HD, where they don't really have treatment?
I think those are very different diseases, and
Sure.
so primary nerve diseases are a different kettle of fish, so with their own set of problems. But I think more globally, this is a challenge for stem cell therapies. There are very few cells that know where to go and how to interact in the right environment, and muscle is one of them. Skeletal muscle. So,
Thank you.
Any other questions for Helen? Thank you so much for a fascinating talk, and we look forward to hearing how the work progresses going forward.
thank you. I want to take this opportunity to thank Dean Miner and to say how delighted I am that you've come to Stanford. And I'm sure I'm looking forward to wonderful times working with you and building Stanford's programs. And I'd also like to thank CERN for funding so much of this research in my lab in developing, learning about the muscle stem cells and working on the human muscle stem cell that has enabled this. Thank you very much.
Thank you for the great work you do.
Thank you.